I'm Jonas Bonér. I'm the CTO of Typesafe. Been involved in the open source community for quite some time, and I'm here to talk about resilience. So let's get right to it. We have a lot of ground to cover. So how many of you would like to go to production? There should be sound. Anyway, I just turned this up then. How many of you would like to go to production with an application that is beautiful, responsive, scalable, highly concurrent, resource efficient, loosely coupled, well, yada, yada, yada. Well, we all do, right? And guess what? None of that matters unless your application is actually up, if it's actually available. So, I mean, really, without resilience, nothing else matters, really. It starts and ends with resilience. So, most of you probably recognize this song. At least some of you, I hope. I mean, it's from one of my old-time favorite movies since I was a kid, Rocky, the first movie. And this is like it's a theme. It's the theme song. And if you don't know the Rocky movies, it's about this underdog. Media calls him the Italian stallion, and he gets a shot at the title. And some of you might remember this quote. It's one of the most memorable ones. But it ain't how hard you get hit, but it's how hard you can get hit and keep moving forward. How much you can take and keep moving forward. That's how winning is done. This is fault tolerance, right? You get hit, you hopefully survive, you limp along for a while, and hopefully eventually you will win. Well, often you don't, like Rocky actually didn't do in this movie. The problem is that fault tolerance, in my opinion, is not a sustainable strategy. Still, we talk a lot about it. Actually, what we need, and what I'm going to talk about in this talk, is resilience. And resilience is beyond fault tolerance. So we're going to cover what resilience is, why it's needed, how other industries, and like in sciences, more sciences probably industries are dealing with it, and what we can learn from that and apply that in the context of software development. So that's sort of the story for today. So what is resilience? According to Merriam-Webster, it's the ability of a substance or object to spring back into shape, the capacity to recover quickly from difficulties. It's not just to limp along like Rocky, right, and so on, but it's actually to be able to fully restore original functionality in order to take yet another beating and yet another beating, right? Not just to survive. Some of you might have heard about anti-fragility. It was popularized by the writer in NASA, Nicholas Taleb, and it's defined as anti-fragility is beyond resilience and robustness. The resilient resists shocks and stays the same, while anti-fragile gets better. It really defines systems that increase the resilience or the capacity to deal with failure when it's getting hit. It gets harder and harder, just like human bones. You know, they get harder and harder and harder and can take more and more hit, right? But I really believe that we have a long way to go in computer science, and I mean this all leads into like adaptive systems that introspect themselves and so on. And we're not really there yet. So I'm going to focus on resilience in this talk, even though I find this concept sort of extremely interesting and exciting and intriguing. Hopefully we will get here as an industry, but we are a very young industry compared to a lot of other sciences. So we need to have a little bit of patience, right? Sidney Dekker said that we can model and understand in isolation, but when released into competitive, nominally regulated societies, their connections proliferate, their interactions and interdependencies multiply, and their complexities mushroom, and we are caught short. This is from Sidney Dekker's great book, Drift into Failure. It's a really good read. It's not tied to computer science at all, but there's a lot to learn here. But at the essence of this quote, the way I read in it is like modeling the world is extremely hard. And software systems, at least most of the ones we write and see out here, are incredibly complex. And I think to really understand resilience in computer systems, we need to understand what it means to create a resilient, complex system. But what is complex then, and how is it different from complicated? This is a complicated system. Complicated systems usually have many different parts. I mean, they're actually all different, and each one has a precise role in the machinery somehow. And it's possible, usually very hard, but it's actually possible to fully comprehend a complicated system. A complex system, though, instead is made of many similar interacting parts, where you have simple individual rules that sort of leads to emergent properties. And it's the interactions that actually produces a globally coherent and interesting behavior. And it's by definition impossible to understand. This is game of life. You know, it has extremely simple rules, but a kid can understand them. Well, but once you start putting them together, they can create an incredibly complex behavior that's impossible to understand, and even more impossible to predict. Okay? And so complicated is not the same thing as complex. That's very important to understand. And Donella Meadows, I don't know if you know, she's written a lot of she's written a lot of good books about and done a lot of research on thinking in systems and system thinking. She wrote about points for human intervention in complex systems. I mean, where humans actually go in and try to turn the knobs. And she writes, and I quote, "Counterintuitive. That's Jay Forrester's word to describe complex systems. Leverage points are not intuitive. Or if they are, we, as humans, then intuitively use them backwards, systematically worsening whatever problems we are trying to solve. Usually humans just makes it worse, because we can't comprehend systems like this. It's impossible. By definition, impossible. Okay? So instead, we need good models to learn how to think and understand failure in complex systems, why it happens, and what we can do about it. And we're really always operating at the edge of failure. This is actually the title of a really good talk by Richard Cook. He wrote about it in this paper as well. I have by the way, everything I'm talking about here, I'm referencing in the long list at the end. If you're interested, we're going to share the slides afterwards. If you want to dive into this as well. And this is a great talk, and Richard does a lot better job talking about this than I'm doing. But I found this model of understanding why failure happens extremely enlightening to me. So I'm just going to share it with you. Okay, Richard Cook, by the way, he's an MD doctor researcher that's been studying resilience in medical systems for 20 years or more. So in this model that his colleague Rasmussen came up with in '97, we have three different boundaries. First, we have the economic failure boundary. We, as a business, we need to stay within this boundary. If you cross this boundary and go outside, then you go out of business. Money runs out. Okay. Then we have the unacceptable workload boundary. This means that if you cross this, you can't produce any useful work. You most likely fall asleep, or like you're fully exhausted, burned out, or and so on. But this actually happens, you know. Startups shipping 1.0, or like battlefield situations, or like catastrophes, or stuff like that. And then you have the accident boundary. If you cross this boundary, then you fail. For some definition of failure, it can be, you know. No money's lost, no outages. If it's medical system, the patient doesn't die, and things like that. And then we have an operating point, and this operating point moves within these boundaries. It constantly is moving because business changes, right? And the different pressure is changing. And if we cross this boundary again, we have failure. Okay, so now what can we do with this? Yeah, we have three different pressures. And the first pressure is like management is always, you know, trying to minimize the risk of going out of business, pushing for more economic efficiency. And then we have the gradient towards least effort. I mean, we as humans, we don't want to do more than absolutely necessary. We want to go home to our families and just get things done, right? And not do more. We're lazy by definition. And then we have the so sorry. So, and these two then naturally like tend to push the operating point towards the accident boundary, just naturally. Okay, and then when we cross this boundary and we have some sort of outage, then everyone panics, right? We say, oh, we need blame the software, blame the architecture, blame the processes. So we start to change a bunch of stuff, I don't know, the processes, the rules, or something like that, and that pushes the operating point like closer to the middle again. But then time passes and we forget about it, and the operating point starts to drift again towards the accident boundary. So history repeats itself. So you might wonder then, why don't we have sort of failures all the time? You should expect this drifting and crossing this operating so the accident boundary all the time. It's actually because we add, normally just intuitively, what we call the marginal boundary here. So we have an error margin. And this margin is usually defined by some sort of rules. It can be speed limits on the road. It can be, we're not going to accept more users than this simultaneously, and so on. And when we start moving close towards this virtual boundary, then we realize, okay, we need to do something, and this means that we are likely not to actually cross the error margin. So then the question: if we have this marginal boundary, then this error margin, how come we still have failures, outages, and things like that? It's actually because we usually know a lot about the marginal boundary because we have defined it. That's tangible. Even though it's virtual, it's actually tangible because we have defined, the numbers and stuff that defines this. But we knew very, very little about this accident boundary. It's not until we actually cross it that we know, oh, here's where the accident boundary is. I didn't know that. We make a note of that, but then that easily fades away and so on, And the economic, the push towards economic efficiency means that we always try to cross this boundary. I mean, Richard Cook he makes this great example of a little kid that you say you're standing at the stove and you have a 3-year-old. I say don't come close here, and the kid you can't cross this that line here, and he walks straight up to the line right there, and when he don't look, he takes one step and then one step back. And then next time, one step and one step back, and soon as within a few minutes, he's standing right next to you in the kitchen. And this is exactly how we do it, right? We try to cross the boundary, and then take a step back and try to cross the boundary. And after a while, we've been doing it so many times, so it feels natural. I mean, we've been doing it for 2 months now, nothing happened, and then we move the boundary, So this is what we call normalization of deviance. Diane Vaughan wrote about this in the Challenger launch decision, when they sort of examined what actually caused them to push the error margin so far that the Challenger, the rocket ship actually exploded. It's also called flirting with the margin, and we get closer and closer and closer, and after a while we've crossed the accident boundary. And we're back to zero and need to start over again. Okay, and I think since we're always operating at the edge of failure, we need to learn to fully embrace failure. I believe we need to design for failure from the start. We need to have a way of managing failure instead of trying to prevent it. Okay, so let's look at how some other sciences manage failure. So starting with resilience in social systems, a friend of mine that does research in social ecological systems and energy efficiencies and stuff like that sent me this great paper. It's a very interesting one in my opinion. It's called Dealing with Insecurity, Understanding Vital Services and How They Keep Us Safe. And it defines, we as individuals, we have 6 ways to die, 3 sets of essential services, and 7 layers of protection. And the 6 ways to die is that we can die from being too hot, too cold, hunger, thirst, illness, or injury. And then we have 3 core set of services, essential services around us as humans, to help us prevent from dying. and that is shelter. Shelter can help us against being too hot and too cold. We have supply. You can see here are the different ones, like the slices of the pie. By the way, sorry, are the sort of the ways you can die. And then we have, as I say, supply is against hunger and thirst, and safety prevents us from illness and injury. And these services are then laid out across in different layers to prevent us from dying. So we have 7 layers of infrastructure. There might be more, right? But this paper defines 7 layers of infrastructure that prevents us from dying. So going from the top, we have the world, for example. Can be like markets, like food markets, energy markets, fuel markets, and so on. And we have the country. They can be like the police. No, so the military. I mean, the regional can be the police. City, yeah, we have hospitals and water plants and stuff like that. The neighborhood, we have like food shops. We can go and buy stuff, food, you know. Our home, yeah, we have our house. We have heating, refrigerator, cooling, all these things. And then all the way down to the individual. So we are like protected by these layers of infrastructure that we don't even think about to prevent us from the worst outcome, being dying. And I think this model is very interesting. I'll come back to that later in this talk, and we'll try to apply it to software engineering. Reinhard Biggs defines 7 principles for building resilience in general in social systems. And the first one is maintain diversity and redundancy. You know, systems with many components are usually a lot more resilient than systems with few components because that if you have many components, that means that some components can compensate for the failure in others. It gives you sort of an insurance policy, like, you know, the saying, don't put all the eggs in the same basket. Managed connectivity is another one. You know, connectivity can be both good and bad. It means like that you can actually recover more quickly and learn about failures, but it also means that disturbances spread more rapidly in the system. So it's not all good, but it's a core trait for resilient social systems. And the other one is sort of manage slow variables and feedbacks. You know, feedbacks can sort of both help us, you know, reinforce and dampen. So it's also important to know what to deal with here. In general, foster complex adaptive systems thinking. These systems, they introspect and they adapt and learn as well. As I said, we're probably not there in general when it comes to software systems, but I think hopefully we're getting there. I've been doing a lot of reading, like about, you know, classic control theory and stuff like that, trying to apply that to distributed systems. But we have, as I said, a lot of work to do. Without going through the rest, I'm just going to dive into resilience in biological systems. I learned a really interesting story about meerkats when I did some research on this, and it was from this TED talk by Nicholas Peroni on complexity theory, and it's a story about meerkats. You know, I personally really love meerkats. I think they're really cute and funny, and they are. I've actually got carried away a little bit and did a lot of study on meerkats, and they are extremely social animals. They have extremely complex behaviors, and it's. I won't go off too much of a tangent here, but you know they have. It's only the dominant couple in the colony, in the family or the group that are allowed to have babies. All the other ones are supposed to be servants and, you know, babysitters. And I think that's one of the really interesting things. And in this experiment, GPS trackers were added to everyone in the meerkat colony, and they were observed going from one feeding place to the next. And it was the dominant female that led the whole group to a road that they had to cross to get to the next feeding place. But then when she got to the road, she stopped, and she gave way for all the subordinates to cross the road and to ensure that was safe. If they didn't come back, I mean, or she could see them being hit by the road, she knew, okay, I mean, probably shouldn't cross this road. So it was like a way of ensuring that she was safe by delegating to others. Okay. And it's actually nature that has sort of evolved this practice for thousands of years, because the dominant female, she's the only one that can have babies. She's extremely important to the group. So these patterns have evolved like as a way of improving resilience. And I think this is a very interesting behavior that I will come back to as well to when I talk about resilience in software systems. So what can we learn from resilience in biological systems? I mean, the first top ones, as actually, I mean, I have to say, I have all the quotes. It's nothing just that I'm just making up. The top one is, yet again, feature diversity and redundancy. And the second one, having yet again, like make sure that your system is really well connected in this sort of network structure, where you have wide distribution across all scales, and you have the capacity to self-heal, to adapt, and self-organize. So very similar to the top four of resilience in social systems. And Nicholas Prone sums it up pretty well. He says animals show extraordinary social complexity. This allows them to adapt and respond to changes in their environment. In 3 words, in the animal kingdom, simplicity leads to complexity that leads to resilience. And I think we have a lot to learn here when it comes to resilience in computer systems or software systems as well. So I covered I took up like half of the time up till now to see what we can learn, and now to try to apply some of these techniques now and ideas into computer systems and see where we land. Okay. Unfortunately, we often react something like this. First not at all, and then with complete panic. And this is actually a great paper that I really encourage you all to read, How Complex Systems Fail by Richard Cook. I think this is probably the most important wisdom in this talk. So if you remember one thing, remember this. That complex systems always run in degraded mode. Complex systems, meaning almost any software systems, always run as broken systems. Okay? They're always failing somewhere. That's a fact. We shouldn't even try to prevent that from happening because it's a fact, I believe. Instead, we should make sure that we build systems that are resilient by design. So the most fundamental lesson that I learned on my journey towards building resilient systems is that resilience is nothing you can bolt on afterwards, even though we've been historically trying to do that for way too long. Sometimes buying expensive tools, turn on clustering, logic or whatever, hope for the best, It never, ever works. It just costs you a bunch of money. This is actually, this picture is from a home in Gilchrist, Texas. This home was designed to resist floodwaters, and it was one of the few houses that survived the Hurricane Ike in 2008. Just because it was designed for resilience from ground up. Okay, so now let's look at some patterns and strategies for how to manage failure. I really think that we fundamentally have to change the way we think about failure. Failure is inevitable. It's actually something natural. Failures are called exceptions in Java and Scala and C++. It's a terrible name. There's nothing exceptional about failures. Something natural. It will happen. It will always happen in a complex software system somewhere. And since it is completely natural, we should just look at this as a natural state in the application's lifecycle. You start it up, you stop it, you might resume it, you upgrade it, and it fails. And if it's part of the regular life cycle of the application, when you end up in the failure state in your state machine, there's nothing to be upset about. You know exactly how to get there. You actually expected that to happen. Okay, so I think we need to start designing for failure and fully embrace it and find a way to manage it. Richard Cook also in this paper says that post-accident attribution to a root cause is fundamentally wrong because overt failure requires multiple faults. There is no isolated cause of an accident. What he's saying that is there's really no root cause, not in a complex system. Don't spend time looking for it. You might find something that comes up. You might find a credible story, but it won't help you much, I think. You most often will be wrong, and it will often even make misleading, actually. Instead, I think you should spend your time thinking about strategies how to manage failure instead and get out of the failure state and learn from that. One core philosophy is to embrace crash-only software. This is the name of a paper by Candia and Fox. And it's a very simple model where you, if you distill down the paper to just one sentence, it's essentially that stop is crash safely. Just crash when you want to stop the application. Start is recover fast, essentially. And this can help us recover from like deterministic bugs caused by inconsistent state. And it's really like having a sledgehammer to the problem. I agree. At least if you apply that to coarse grain level, but it's a very useful one. And also, I just want to, since I'm on this paper now, I just want to read up a quote that I think was really important and will tie into protocols that I'm going to talk about later. And I quote, "To make a system of interconnected components crash only, it must be designed so that components can tolerate the crashes and temporary unavailability of their peers. This means that 1, we need strong modularity with relatively impermeable component boundaries. 2, we need timeout-based communication and lease-based resource allocation. And 3, we need self-describing requests that carry time to live and information whether they're idempotent or not." I really think this is something we should take with us when we design protocols. And you might have heard about this like let it crash idea, popularized by Joe Armstrong and Earl Langensohr. It's really fully embracing the crash only approach to failure management. But these authors, Candier and Fox, they didn't stop there. They in a follow-up paper that called Recursive Restartability, turning this crash only sledgehammer into scalpel. They argue that you should apply this crash only pattern to any level of granularity, recursively if needed, and it often is needed. And I really believe that this way of looking at it is a very powerful model. It allows us to write systems that sort of gracefully tolerate restarts at any level, usually from inwards and up. It's also a pattern that I will come back to later. Another great quote from this paper, Recursive Restartability paper, is that software components should be designed such they can deny service for any request or call. Then, if underlying components can say no, then apps using that must be designed to take no for an answer. How to decide to proceed, give up, wait, retry, reduce fidelity, etc. I think what they're saying here is that services, they must be allowed to say no. I can't keep up any longer. And this also means that the components using that might need to be able to cope with being told no and know how to proceed. And almost all failures, what I talked about here, and the reason driving this crash-only view of the world is that almost all failures relate to some sort of state, data. We have inconsistent state, like partial state, wrong state, wrong data, lost data, duplication of data, and so on. And let's try to classify what we mean by state. Okay. First, this is like my classification. I didn't make this up. This was something that I learned and found useful. Is that first we have static data. That's the data that you can read from config files and like we read from like a stable storage somewhere. That it doesn't change, it's always available, you can always read it in and so on. Then we have scratch data, that's data that you use in computations, like temporary data that you use to get a result. If you lose that, that's fine. And then you have dynamic data, and dynamic data can be divided into two sort of categories. You have recomputable ones that sort of based on static data, sort of variation of static data. But then you have the not recomputable, and this is your critical state. If you lose this, then you're a host, right? This can be user input data, for example. It's hard to go out to ask the user, can you like fill in the form again for me, please, or stuff like that. Sure, no one probably dies, right? But it's still, it's not an ideal word to lose not recomputable data, because you can't provide the level of service that you hope to do. Okay, so now let's take a look at traditional state management that we've sort of all been sort of used to use and have learned to use. So the legend here is that this blue ball here is an object of some sort. The white one is a client, and this red box is critical state that you can't lose. I mean, if you lose that, then you can't provide the level of service you like. And this dotted line here is a thread boundary. Okay. So often, a regular object system you look something like this. You have a whole bunch of connected objects with the critical states a little bit everywhere. I I mean, somewhere around this object graph. And now, if a client makes a request, it leads to some activity down the line, you know, and in traditional systems, at least the way I wrote them, like 10 years ago or 20 years ago or so on, when I started this career, was that they all, I mean, do synchronous requests. So you have this call chain, you know, stack frame after stack frame to another object, to another object, to another object. Now, what if something fails, you know, down here, for example, down at the bottom here? The problem then is that the whole stack is blown, right? One object failed, it needs a cascading failure to the next component. So the whole stack frame is blown all the way up. And the problem is that if you don't do much about it, then all you get is like that thrown right in the client's face. And if there's really no client, all you see probably is a log, you know, out to the like with exception, you know, printed out all the way up to the new thread or the executor service or something or something like that. Then it's complete silence. And the problem is that this is the failure management that we've grown up with. But I really believe that is really completely, utterly broken. Because if a thread blows up, you know, that's the only context you have. So if your thread blows up, then you lose complete knowledge about what happened, why something went wrong. You have to go ask the client then or something like that. And since this context is the only context you have, you need to hold on to that as much as you. My bag went down there anyway. Hold on to that like as much as you just can, because you just simply cannot lose it, because exceptions don't propagate between contexts, between threads, between other components, unless you actually ask it to do. So what you have to do then, you need to since failures can happen anywhere, you need to be prepared to handle failure anywhere in the application. You need to go around and like sprinkle around try-catch statements almost anywhere and be ready to deal with failure anywhere in the application. You know, and that's where you get systems like where often your business logic completely tangled with error handling, and often more error handling than actually business logic. And it's also scattered across the whole application. It's a cross-cutting concern. I used to do aspect-oriented programming. We actually try to deal with that, you know, extracting that out into like what we call the third dimension and stuff like that. Very cool stuff. But it didn't work much because it's delegating the problem, you know. It's still based on try-catch statements, just weave into the code. So I believe we need a better way of dealing with this. Don't code defensively like this. Failure is natural. We shouldn't try to protect ourselves constantly from it to happen. I think structure can bring sanity back. And as Sidney Dekker said, that accidents, they come from relationships, not broken parts. It's the relationships that takes down your system. Okay. So I think the requirements in my book for sane failure management is the failure first need to be contained. So you can't get you can't get these cascading failures where errors just spread completely without control. So the errors need to be able to reify. You know, it's sort of the computer term for being turned into something tangible, something that you can touch. They need to be turned into messages. And if they are messages, that means that they can be signaled in an asynchronous fashion, you know, to anyone that's interested. There might be others than the client being interested. The client actually might not even be interested. He doesn't care if the service can't use another service out there. Why should he care, right? He might care if you put in the wrong password and so on. I'll come back to this later. But you know, failure should be signaled to anyone that's interested in it. And these should be able to observe it. And if they can observe it from a context outside the failing context, a safe context, another component running another thread on another machine or somewhere else, just not in the failed context, then they can do something about it. Then they can manage failure. Okay? And so first we need a way to contain failure. The bulkhead pattern is a very good pattern here. It avoids failures from leaking and called cascading failures. It's actually the way the ship industry have constructed ships for hundreds of years. And the key here is compartmentalization, where you divide your ship into discrete and fully contained compartments here. So if one or two or three of them sort of starting to fill in water, the whole ship doesn't sink. And when I talk about that, everyone brings up, yeah, but what about Titanic? Isn't that a counter example? Actually not, because what the Titanic did, it didn't have these walls go all the way up. So when 3 or 4, I don't remember what it was, but enough, what got filled up, so it started to tilt. Water started to spill over to the next one, to the next one, to the next one. So Titanic is actually a great example of cascading failure and happening when isolation is not fully happening. Okay. But I really believe that this way of dealing with failure is yet again back to fault tolerance. Because you get hurt and you can limp along. But I think still yet another time, yet again, I think we can do better. I think we are in a position to heal these compartments and can actually come back to fully resilient systems. And to do that, we need to enter what I call supervision. The supervisor is a guy that listens to the failures in a safe outside context, right? And he is able to fully respond to that. So the supervisor can learn about the failure and can choose to restore, resume, or restart the failed component to restore full service again. There might be a temporary hiccup, but after a while the system can restore full functionality and really self-heal. And let me explain. I think I have 15 minutes left. I should be able to go through this. Let me explain how this works through a practical example that I use, that I sometimes tell, and it's about how a vending machine works. So you have this programmer. He's really eager for coffee. He's been sitting hacking all day, and he walks up to this coffee machine and he puts in like 1 quarter, for example, and 1 kronor in Swedish or Danish, and let's say it costs 2. Right? What's happening? The coffee machine will display an error message right in the programmer's face saying, please add more coins or something like that. Then the programmer adds all the coins, meaning he fulfills his contract of the service and he gets his coffee. And the programmer is happy. Now the next day he walks in and inserts 2 coins. And now he gets like an out of coffee beans error thrown in his face, or like out of water, or like bean jam exception, or something like that. What should he do with that? I mean, where is the key to the machine? Where is the beans, right? Or how can I fix the grinder? That's not the programmer's responsibility, and that's usually not the way it works either. I think that's just completely wrong. Instead, what's happening in an ideal world, I don't know if this is really the way it's happening, but is that there's this service guy who runs around the floors, in the office, and he asks for a beeper, perhaps something like that, and he gets notified that something's wrong with his coffee machine. It actually might be, periodically in real life. So he comes the next day and discovers it. But let's say that he has a way of getting signaled. He is the guy that is responsible for this coffee machine. So he's the guy that should fix it, add more beans, for example. And the programmer gets his coffee and is happy. The important thing here is that we need to distinguish between errors that the programmer is responsible for and failures of the service that the programmer shouldn't have anything to do with. He shouldn't even be aware that this is happening. Sure, if it's a long delay, it might be nice to notify him that something that's going to be fixed in a short time, but it's not his responsibility to fix this. And I really think that this is the way we should build systems. We have request response validation errors. Clients not fulfilling their contract should be thrown right in the client's face. But not everything, like this synchronous try-catch model encourages, that we throw everything right at the client's face. Because what should he do with all of these things? These should go to a supervisor that should deal with the error. And as I program a lot with actors, for example, and in the actor model, it is a supervisor that creates his workers. And naturally, since he created the workers, he should know how to deal with errors in them. He should know that these my workers here, they use a third-party service here, for example. If that's going down, I have some clue what's going on at least, and I should be able to deal with that. So I think the model where the guy that creates the service is responsible for it, and the failure of it is a good model. So I really like what I call then sort of the error kernel path or onion layer state failure management. This is also something that I think I learned about in Erlang the first time, where they're like all in on this way of working. And we have in Akka, the project that I started some time ago, we have also fully embraced this model. And the model is that instead of having our critical state scattered across the whole application, we instead contain it in what we call the error kernel. It's a minimal sort of minimum, we'll say, sort of place where we put everything, and that's sort of in the innermost of this onion. Here is where we put our critical state, and then we have layers, of defense protecting us here. So this means that whenever something's going on, can hardly see here, right? But let's go back here. Whenever this component is supposed to do something dangerous, he never does it himself. Instead, he delegates, to this layer here. That might also delegate to this layer. That might also delegate, right? So you have these layers of defense. So whenever a request is hits the error kernel, you can always assume correctness. Then it's been fully validated. I mean, all these dependencies have been fully checked. Nothing can go wrong here in an ideal world. I mean, you can there might be bugs, it can get out of memory exceptions or whatever. Someone might just pull the plug of the machine, right? So, but in theory, when a request hits here, everything is fine. So let's take a look at an example here instead of what I call onion layer state management. It's still a traditional state management. Here you have all the critical state in what I call the error kernel. And then you have layers of defense, you might say. Layers of services protecting each sort of service higher up. And now the interesting thing is that each one of these services runs in its own thread. And the reason for that is just not, you get concurrency and you can scale things out. I mean, that might be nice, but the thing is the key here is that this gives you a safe boundary. That means that if this thing fails, it doesn't affect the rest. It's fully contained. Okay? Think about these like machines, like running physical machines, like running. You can pull the plug on one, no big deal, nothing happens. It doesn't cascade. So now, if a client hits one of these, and something then goes wrong, then a notification will send up. The whole connection all the way up to supervisor will burn. It will be notified, and the supervisor can take action by restarting this component. And the client can continue using him. Retry he has to do. And I sound like Yoda. but the next time he will that will be a healthy component. And the interesting thing is that if his parent can't deal with it, then he can just delegate or escalate. Sorry. So it might be that there is an error that none of these layers can actually deal with, and that will hit the error kernel. But at least we did as best as we could. Like, for example, an out-of-memory error. It's really hard to deal with that in Java. That will hit the error kernel. But that I'll come back to that. So as you've probably seen, like this way of working is very similar to how the meerkats is actually dealing with resilience. With the female. With the dominant female, stops at the road. This is risky business, and start delegating to his poor subordinate. Like, let them run out of the road to die to check if something is working. This is exactly the same thing. By one of these things doesn't perform dangerous work, delegate, and watches what's really happening here. Is something going wrong or not? No, it didn't. Everything's fine, and I can continue to process the request. And this way of working, this sort of onion layer state management, is very similar to how the world actually works around us, where we have these layers of infrastructure protecting us individuals without really thinking about it. So I really believe that it's a natural model to deal with resilience that is really natural to a lot of us. But this is not sufficient, actually, because because we need to maintain diversity and redundancy. This means that you can't just bet on that your machine will just be always up. The machine might actually fail. You can never run a resilient system with just a single machine. Like the cleaning lady, like my colleague Roland, he actually told me. I don't have that much time, but this is a funny anecdote. He actually told me that he is a physicist, and they were doing this overnight experiment, like calculations, and they had like full redundancy, 2 different machines, all plugged in. But the cleaning lady, but what they didn't expect was at the night the cleaning lady came up and actually pulled both plugs and started like swiping the floor and then pulled them back and then plugged them back in, right? So I mean. You can never expect all failure scenarios in a way, right? But having more than one machine actually usually helps a lot. And as we all know, I mean, if you start running things on multiple machines, then you have a distributed system, like most systems today are, even if we don't want it or not. They are distributed systems. And as soon as you have the network, weird things start to happen. The network is actually not reliable. We have you have to deal with partial failures, messages, which actually is the underlying communication between nodes over the network. It means that the messages can be delayed, lost, or reordered, duplicated. There's a lot of things that can go wrong, and failure detection just turns into a guessing game. You just cannot simply know if a node is down, or if it's just doing GC, or is having being overloaded, or something like that. You have to guess, take educated guesses of if your services are up or down. So it's a very different world, and in this different world, I actually did a whole talk about this, so I won't go into too much detail, called Life Beyond the Illusion of Present, but I really believe that strong consistency is the wrong default. We might need this in the rare circumstances, but this is not the way we should fully embrace and do and design software. Because I really believe the systems, they need to be decoupled in time, meaning that the sender and receiver are decoupled in time. This means that you have this asynchronous boundary, this safe haven. So all of these are running in like safe boxes, safe havens, you can say. And this gives you concurrency and asynchronous message passing. It gives you this loose coupling, and service share nothing design. And they need to be also decoupled in space. That means that you get distribution, not just concurrency through interleaving, which is actually decoupling in time, but actually you have to be able to run things in multiple contexts, decoupled in space. And here reactive principles lead the way. I also think that in order to really conquer this distributed world, we need to have resilient protocols. And in my experience, resilient protocols depend on 2 things: the asynchronous communication and eventual consistency. Because protocols like this are tolerant to message loss, message reordering, and message duplication. And there's been one of these terms that's sort of come up, sort of a little funky term called ACID 2.0. I don't know if you've heard about that. Most people know what ACID is: atomic, consistent, isolated, durable. ACID 2.0 sort of changes the meaning of this acronym into A standing for associative, meaning that it's batch insensitive. You can batch and group as you want. C stands for commutative, meaning that it is order insensitive. Ordering doesn't matter. And I stands for idempotent, meaning that duplication doesn't matter. So it's fully embracing this way of designing protocols actually can lead to a lot more resilient protocols. And we should not strive for transactional semantics. Then going back to testing, ending with some words on testing. I really think that we have a lot to learn from Arnold. I think we should just learn to just blow things up. We really shouldn't be worried about that. Like, shoot down your application, understand when it breaks, where it breaks, how it breaks. I think just simply pull the plug. I mean, the Ethernet cables, or there are great software actually that helps you with this. See what happened. Take notes, because often the results will completely surprise you. Things will not break where you expected them to. Especially not in the complex distributed systems. As I said, there's a lot of great tools. Here's just for some of them. Netflix has this Simian Army. Akka has multi-JVM tests. All of these can like simulate network outages and like do all kinds of crazy stuff. Messing around with a network, dropping messages, delaying messages, slowing messages down, etc. And you have like tools for trying to shoot down your application, like Gatling here and stuff like that. And yet again, I think you should design for failure, and you should like test it as any other code that you test. I mean, sometimes it might actually be worth to go like to do like Netflix, go all in and even test in production, like they do, because nothing beats production. It's a completely different world as soon as you go to production. So I've covered a lot. I just want to sum things up. As I said, one of the biggest thing, or main things I want you to remember is that complex systems always run as broken systems. It's always something failing somewhere. And the only way out of that, is to fully embrace resilience as something that you design for and design with, right? The resilience is really by design. It's nothing you can bolt on afterwards. You need to think about it from day one and see it as a natural state in the application's life cycle. That's everything I had. Thank you. And I